I'm going to talk you through the max power theorem today, which is a really useful way of analysing how real power supplies behave. It can tell us the internal resistance and, importantly, the conditions at which we're going to get a maximum power output.
Gorilla physics!
So, just to remind you, we did a setup like this. We're interested in this internal resistance here. And what we did is vary the load resistance and took readings of I and V. Now, if you haven't done that or you haven't seen that, then go ahead and find my video on measuring the internal resistance of a power supply. I'm going to use the same data from that video to actually analyse this. You're just taking readings of V and I as you vary load resistance, and we're trying to work out the internal resistance here. And once we had our readings of I and V, we can actually use them to create a range of values for the power in this circuit and a range of values for the resistance on our variable resistor. And we're actually plotting R against P. Okay, and you get this distribution here, which is very interesting. And we're interested in this point here, which is the maximum power output of our cell. Now, I'm going to go into calculus now, and I'm going to show you how we can work out, or how we can show that that must be a point at which R, the load resistance, is equal to little r. So whatever the resistance here on the graph is the resistance, the internal resistance of our power supply. Now, if you're not studying A-level maths, then maybe calculus is going to be a step too far from you. So you can just take it as being, well, this theory does show that the maximum power output is a situation where the load resistance is equal to the internal resistance. And you can kind of imagine that about the electrons flowing, that they've got the same resistance here and here, so there's the same impedance throughout the circuit, so there is a maximum power output. They're not having to kind of slow down and speed up if you like. You can kind of stop here. But as a famous physicist once said, everybody needs a basic grasp of calculus. Wise man. So I've left at the top of the screen here the definitions that we've used so far and the graph. And what the first thing we're going to do is to derive a new equation for power, which involves the current and the resistance. Now that's a simple derivation. It's simply rearranging this for V and inputting that in this equation instead of V. This is our definition for power, which is relating power to resistance. And from that, we're going to get our equation of our line and then do our differentiation. So now the next thing to do is the definition of an EMF. An EMF is the current multiplied by the total resistance in the circuit. In other words, the load resistance plus the internal resistance. And from this, we can derive another equation which will relate power to the two resistances. So if I rearrange this for current, if I rearrange this for I get EMF over R plus R. And I simply insert that into this equation here. So I've got to square all this when I put it in. Copy the product down there. Okay, this is the equation for that relationship there. And we're interested in this stationary point. And the stationary point is a point at which the gradient is 0. Now, dy by dx, you'll know, is your notation for differentiation, the differential. But in this case, on the y-axis is p. And on the x-axis is r. So what we're going to do is differentiate this equation, P, with respect to R. But the process is the same as you'll have done in maths with your y's and your x's. So now I'd just like to say thank you to Zain Patel, who pointed out the way to differentiate a fraction is to use what's called the quotient rule. And the quotient rule says that differentiation of a fraction, and we're going to call that fraction fx over gx, just two functions of x, with respect to x, is gx multiplied by the differential of fx, take away fx, multiplied by the differential of gx, over gx squared. So that's what I'm going to have to do to differentiate this function here. So the first thing I'm going to do is I'm going to actually get gx, differential of g, fx and differential of x ready so that I can just input them into the fraction. Okay, so let's go ahead and get all my terms ready. So firstly, fx, that's the top one, just as it is. And then the differential of fx, which is, well, multiplied by the original power, reduce the power of r. Remember, I'm differentiating with respect to r here. Just e squared then. Then gx, which is just the bottom line there. And the differential of gx. Now here's where I need to actually expand that bracket there into its quadratic. So that's r squared plus 2r little r plus r squared. And now I can differentiate that. So times by the original power, then reduce the power of r, times by the original power of r, which is 1, and then reduce the power of r, which gets rid of it. And this, in this case, has no powers of r, so times by 0. So if you like, plus 0, but we just don't need to bother with that there, do we? So now I'm ready to write my equation for dp over dr. Gx, so all of that. Times the differential of x. Take away fx, which is this one, times by the differential of gx, which is here, all over gx here squared. Now I'm going to use the factorised form here because, as you'll see, that's that, and I need to square all that. My next line, that's going to be much easier for me. Right, I'm going to delete my quotient rule down here and tidy up my board a little bit. Okay, now I'm going to expand and then simplify. So let's expand this. Okay, and remember that is all over this here, and here I can just add the indices. So we'll multiply the indices. Okay, so that allows me just to write down a simpler form then of my differential of p with respect to r. I've got e squared r squared minus e squared r squared, and that's all over r plus r to the 4. There are some situations where this can equal 0, and remember we are interested in our stationary point, well, actually, this could be infinity, and then that would equal 0. So, in fact, if either of r or little r are infinity, well, then that's going to equal 0. But, of course, that doesn't really seem to make sense to us in our terms of our real-world resistances. So the other possible situation is where the numerator is 0. And because EMF is a constant, the numerator would only be 0 if r and r were the same value. So here this shows that for the maximum power, this stationary point on our observed graph here, then the internal resistance is equal to the load resistance. We can actually show that by separating these here . And then rearranging . And then we have common factors that we can cancel. And obviously we can root both sides to get back to our same situation there. And that's one of the real solutions to that equation there. I hope that made some kind of sense. I think it's a really useful demonstration how what you're doing in maths with your calculus applies to real theories, real physics. And I just want to change my social media hashtag to thank you, Zane, because actually physicists and mathematicians do work together to develop theories. And I didn't know how to apply the quotient rule before today, and I do now, and I've come up with a valid conclusion. So thank you very much for pointing that out. Thank you for watching Gorilla Physics. Please do like, share and subscribe. That really helps me be more useful to more people. Also, please go ahead and check out Gorilla Chemistry and Gorilla Biology. You can expect the same sorts of things, past paper questions and videos to help you understand topics. Thanks once again for watching.